Hello Abaqus user, welcome to Abaqus Acumen for quick and sound learning. Today's session will be on the manufacturing simulation, and in this particular simulation we are going to do a deep drawing. So right now on my screen what you see in Abaqus viewer is a deep drawing process. So we are going to form a channel. So let me switch off some of the elements of die, punch and holder. So this is what exactly we are going to do. We are going to form a channel. So it's like a deep drawing process. So 1 millimeter by 200 millimeter channel, then we are going to go for a deep drawing process, and this particular tutorial is available in Abaqus help manual. So a couple of people also done this on YouTube, but there are a lot of confusion how to do it. So if you see in the front view, there are like two curvature, and we'll go do this deep drawing. More than 400 MPa is the 400 MPa is yield stress. So whatever more than 400, what you see is going into permanent deformation. So this is exactly we are going to do. So let's go to the drawing board, just quickly see what we are going to do. So we are going to do a deep drawing manufacturing simulation. In deep drawing simulation, we are going to form a channel. So typical arrangement for this particular thing is you have blank. So for our particular case, it will be 1 millimeter by 200 millimeter blank. We'll have a punch, we'll have holder and die. So holder will put a blank holding force of 440 Newton on a blank. So this will be a two-step process. In the first steps, you'll just keep a workpiece, put a blank holder force of 440 Newton, and then we'll give a punch travel of a 30 millimeter, and then we'll see how it is forming, what will be the issue. So that exactly we are going to do. Now looking at this problem, just going back, looking at this problem as a Abaqus community, and what we are teaching for the Abaqus user is, look what are the things we can use and how we can simplify this problem. One thing we can do is we can quickly take a symmetry advantage, so that way you reduce the number of element half. Second thing, actually this is the 200 by a 300 millimeter length channel. So the strain in third direction will be a constant, so you can quickly make it a plane strain problem, again reduce number of DOF without compromising much on the results. So this will be my last slide, and then we'll just quickly go to the Abaqus CAE. So we'll model workpiece. So this is like a 380x steel, 1 millimeter thick, 200 millimeter length. Typical steel property, yield stress is 400. Again, the important thing which also we are talked in a sheet metal bending, this particular problem we are going to do in Abaqus standard. So it will be, solver will be implicit. You can do this in explicit, but when you use explicit, it should be a quasi-static problem where actually the inertia forces should be minimum. A lot of people are doing this problem in explicit without making them a quasi-static problem. So there are a lot of inertia effect, and that will mislead a lot of results. So we are going to do in Abaqus standard, solver will be implicit, so there is no inertia effect, so you don't have to worry much. We'll convert the problem to 2D. Since the perpendicular length, the third length is high, the strain in the third direction is constant, so we'll use a plane strain approach. For plane strain approach, there are CPE4R, so 400 by linear plane strain quadrilateral element will use. Have 3 DOF, XYZ, and Z rotation will take the symmetry. We'll also use a contact damping and automatic stabilization for this problem, because there is quite a bit rigid body motion is there. Again, a word of caution from the Abaqus Acumen: whenever you use a contact damping or automatic stabilization, you should always check what is a stabilization or energy, or what is the damping energy. It should not be more than the 5% of the strain energy developed in the component, otherwise then results are not accurate. So let's go to the drawing board. Again, I'll show one more time this animation. So this is exactly we are going to do. We are going to form a channel. So let's start. So we'll say new, and then I'll just change, I'll set a working directory. So I'll just set working directory. Now first thing we'll create quickly a workpiece. So I'll just go one more time. So we are going to create a, there is a typo, we're going to first create a blank. So we'll create a blank. It will be 2D deformable shell, so like approximate size 300. I'll quickly put 1.0 comma 0, then 100 comma 0, 0 comma minus 1, 100 comma minus 1. I'll quickly create this, and then we are done. So we are done this. I'll also split this in center. The reason I'm going to split in center, because then we have to define some contact here, some contact there. So let's split it in center. So we can split using a datum line. We'll create one datum. So we'll create a YZ plane around 50. So we get a plane here. We're going to quickly we'll cut the face using datum. So we selected datum, create partition, done. So now guys, we have just created a splitted this, because then when you select the edge for contact, it will be easier for us. So we created the blank. We'll quickly create a material. So material will be steel. This will be a 380x steel. Elasticity is like 210 e power 03. 0.3 will be Poisson's ratio, and then we'll put a plasticity data. So like a 400 will be the yield stress. For that will the plastic strain will be 0. Then 420 for that the plastic strain will be 2%, and then 500 for that plasticity will be 0.2, and 600 for that plasticity will be 0.5, means 50%. So we quickly done that. We'll create plane strain. So plane strain, you have to take a solid homogeneous. You created that, and we'll quickly assign this. So done. We assign this. So as soon as you assign it, change the color. Now we'll quickly create holder. We'll call holder. It will be 2D. It will be, you have a different option guys here. You can use a district rigid or analytical rigid. My preference is district rigid. There is no difference. Only for district rigid you can make a mesh, and analytical rigid you don't have a mesh. Abaqus will generate mesh for the analytical rigid. My all the time preference, whenever I have to select from a district rigid or the analytical rigid, I prefer to have a district rigid. Then you can control the mesh. Once you control the mesh properly, you can control the contact. So I'll select the discrete rigid for holder. I'll again 0.0. This will be easy for me to go from origin. Then 60 comma 0, I get another point, and then 0 comma 60. So I get a 3 points. Now I'll just quickly put line. So this is one to this and this, so this will become right angle. Then I'll just give a quickly fillet of 5 millimeter. So fillet is done. So done. So quickly you created a holder. Now this is rigid. Make sure you assign a reference point. So we assign a reference point. We have done that. We'll create now die. Again 2D district. We'll put 0 comma 0, then 60 comma 0 minus 60 comma 0. Sorry, this will be wrong. I'll delete this. The point will be 0 comma minus 60. So I get 1 point at the bottom. So you get this right angle. So I'll quickly create this. I'll go to the fillet, the 5mm fillet. I'll say OK, and this is done. So done, you created that. I'll just attach a reference point here. So you've done that. Now you created a blank die holder. We'll quickly create punch. 2D discrete element. We'll start again from 0, 0. Then it will be like it will be 55 by 55. So it will be 55, 0. So it will be minus 55, 0, and then 0, 55. So there is a different, the blank and the holder will be the same dimension, 60 by 60, right angle, and then you have a fillet there. Punch will be 55 by 55 with a 5mm as a radius. So you've done that. You put a 5, and then you created a fillet. So you've done that. We'll quickly select a reference point. So you've done that. So now I think we created all the component. We assign the blank all the necessary properties. Now we'll quickly make an instance. So we created the instance. Now the one more part actually for this we have to do is we need to shift it everything. So the first thing what we'll do is I'll shift first I'll shift die. So from this point, so this will be my second end point. So okay, so I shifted that. We'll also shift we'll shift first I'll just shift from point. What I'll take a starting point is this curvature starting point. So I select this, I'll just go to this. So this is okay. So we have that. Then I'll also translate this one. I'll translate translate from this point to this point. So they should be aligned to each other. Now one more thing, actually die is penetrating to the workplace, so we need to translate the die by 1mm. So down 1mm. So 0, -1. So this is there. So now it is position everything. I need to, again, there is edge to edge connection is there between the holder and the punch. I need to move it by 1mm. So this 0, 0, 1, 0. So it's move. Similarly, I have to move punch. Sorry, die 1, 0. So now, guys, you see what we have done. We have created a blank. We have created a punch. We have created a blank holder and a die, and then we between this is a 1mm gap, and everything is done. Now we'll quickly create. So for first case, it will have a symmetry boundary condition here on the workpiece. It is symmetric about X. So I'll go and create in this is a symmetry X. So I'll select that and I'll say done. I'll create surface. So I'll create slave 1 blank. For that I'll select this and I'll select control and select other also. So done. I think it is not created, so I'll delete it again. So we'll create slave blank, slave 1 blank. You select this and then select this. So you have to put a shift, then you create. So this is full thing is there. Then we'll create slave 2, which will be this edge and the holder. And the other thing will be this edge and the blank. So let me check once in assembly how they look. So it's okay. So this and this is there in contact, this and this is in contact, so we are done. Now the top full surface we have taken, which will have a contact with a punch, holder, and the half edge will be there, and then die and half edge will be there. Now we'll create a surface on a die. So we'll create surface. So master die. Done. Now this is important thing, guys. So I just flip this, and I'll also flip this. So now everything is same thing, because this normals was different. I just corrected the normal. So I'll select the magenta. So we required the surface which is outer, not an inner surface. So I selected the magenta. This is for die. Then we'll select one for holder. Master holder. We'll select this. We'll select yellow. So this we are done, and then we'll select one for punch. So we'll select yellow. So we created now surface. Now first we created 3 part. We assigned the material property section to this. We are done this surfaces here. We'll quickly do meshing. So for blank, at least we required a 3 element across the thickness. So we'll put global somewhere around 0.25. You say yes, and then you assign all this to a plane strain problem. So standard linear, you come down, you'll see a plane strain problem. By default it is a plane stress. When you get to 2D to plane strain, you say okay, done. You done that. Now we'll quickly select a die, and this is the advantage here with a discrete rigid. So you control here. I'm going to put point to similar mesh here, so that way actually it will have better contact. No contact issue generally you get when you have good fine mesh on the analytical rigid also. you done that. So you created all. Now all everything is ready. Now we'll go to the interaction property. We'll create friction. Friction will be 0.1 for this. So tangential behavior penalty friction, you put a 0.1. Contact control we are going to use automatic stabilization. So automatic stabilization we are going to put some normal 0.002, very minimum factor here, and we'll define contact now. Create, so contact punch and blank. Surface standard contact. So master surface, you punch, you highlight it, so you select, you can see it is highlighted here, and surface you take first blank, so whole blank is taken, so that we are selected, and we are going to connect here the contact control, which will be the damping, contact damping we are going to put. This will be the first, then I'll create two more. Contact holder blank, continue. Done that, we'll create contact die and blank. So die we are selected, and then you selected a blank, and make sure you select here. So done this, so I'll just check whether I selected. Okay, everything is done. Now one more thing we'll do, we'll go to the now loads, boundary condition. First thing we'll do is put a symmetry boundary condition. So symmetry X will be before the step which is applicable for the fourth step. So symmetric boundary condition, you done this, you selected the blank symmetry which is there, and then you see a X symmetry. So we have done that. Quickly we'll create a step. So this will be the holder pressure, holder force. NL jump on, we are going to use automatic stabilization by default, whatever is there for damping. Increment we are going to make 1000. We are going to start with very slow load, and this will be the holder force. So we have created that. We'll also create now, for the first step we'll create a boundary condition for a die. So die will be fixed, so we'll select the die reference point and we'll select die is fixed. Then we'll create, I'm sorry, I have to delete this, it is not, we have to rename, it is not die, it is a punch. We'll create for die will be fixed in alt off. So X, Y and Z rotation, and for holder it will be X and Z rotation, Y it has to free to move. Now I'll quickly apply load, which will be the holder force. It will be concentrated force on this point. So it will be minus 440, and we'll put a follower force. So this is the first step. You have a holder, and then with a blank holder force of 440, the blank will keep. And then second step, there will be the punch movement. So we'll create a second step, punch movement, automatic stabilization on, period, punch stroke, put 1000, this you start 1001, minimum will increase to 7. So we created that. Now one more thing you have to create is you have to change the boundary condition for the punch. So this, if you edit, and here actually the Y stroke of 30 millimeter is there, so it will be modified. So the symmetry boundary condition is before the step, then you fix the die and punch for alt off. You holder, you just keep it X and Z, it's free to move in Y, then you apply the load in that. And for this actually the die is fixed, punch holder, the force is there 440, we modify this. So this is what we are done. I think we are ready to run it. So I'll just create a job name. So let me create, so we'll create channel formation 2. We'll go for a data check. If there is any issue, we can quickly check it. So we'll just wait for a data check. Once we get a data check, we will get confirmed that there is no issue related to preprocessor. So whatever the issue, if comes later part, it might be because of solver issue, it will be convergence issue or anything. So let's wait for a data check. I guess once we have data check done, so data check is done, guys. So we'll submit a run and then wait for the results. So let's submit the run and then wait for results. So guys, the results are out, and right now on my screen what you see, how is the deformed shape, this particular one mass stress we are looking, and then you can see it just taking a shape. So it just bent. So I'll just quickly check at the first step. So this is like a holder pressure you apply, and then we'll just check a field output stress for that. So not much stress generated, and then it is with a punch stroke for 30 millimeter, it start form this bend shape. There are some stresses which is going more than 400, and then this form. So this is 2D now. So we'll just I guess this will help for some of you how to convert into 3D. So you go to ODB display option, you create here a 300. So this will be extended by 300, and then since we are using symmetry, so we'll put that symmetry here. So you'll see a full model. So now you see a full model, how it is forming a channel section. And I'll just remove this all rigid die holder punch. So this is how it is, this is creating. So this is actually is available in Abaqus tutorial. Only lot of complexity is there, the language or method they use. We simplified it, and then this was the one of the video in the metal forming, just to get a deep drawing. So you can try out this with Abaqus standard. So that's it, guys. This is what actually from our side. If you have any query, anything related to Abaqus, related to this tutorial, please send it to abacusacumen@gmail.com. Also, we are doing this community service for Abaqus users, so make sure to like us the video when if you like it, and also don't forget to subscribe us. We need your support to take this project forward. Thanks a lot. Bye bye, and go ahead and try this tutorial. Thank you.